seminar. Welcome to the first presentation in our fall 2021 physics seminar series. It is supported by Eddie and April Lucas, and also today's presentation is on Zoom. We are actually going to have a couple of presenters live in person in this room, Jabara Hall 126, throughout the semester. Next week, we are going to have the welcome back event that will be out on the lawn by Morrison Hall, so we can eat and socialize and not worry about the virus. So if you want a box lunch for that, please let Connie know. We are going to have plenty of extras in case we don't get RSVPs. We'll have those box lunches in the SPS room. You can pick one up and join us on the lawn by Morrison Hall there on that outdoor classroom space. We'll, introduce each other and just talk about all kinds of fun topics. All right, but today we have Caleb Gemar. He was an undergraduate here at Wichita State University and then did his master's with us as well on the New Soul project when that was just ramping up. That's, of course, become an effort with quite a few students on it now. But Caleb moved on after finishing his master's, and he is now a PhD student at the University of Texas, San Antonio. Is that right? Yes. And he's going to talk about the Moon and Charon today, Pluto's largest companion. So Caleb, welcome to the physics seminar.
All right. Yeah, nice to be here today, albeit virtually. So I will go ahead and start sharing my slides. Let's see here. All right, and just one more check to make sure that everyone can see my first slide there. Good. All right. So my presentation today focuses on investigations of planetary surface properties at the Moon and Charon. And the main emphasis on that is, of course, actually far ultraviolet photometric observations, particularly at the Moon, and observations of properties at Pluto's largest moon, Charon, both of which are focusing on laboratory investigations that are done in conjunction with these observations. So first and foremost, everything I do right now is on small solar system bodies. And we have to ask ourselves, why do we actually care about small solar system bodies? I mean, they're for all intents and purposes, most of them rather small featureless rocks out there in space. But the truth is, small solar system bodies actually tell us an awful lot about the history of our solar system. Because they do not have significant atmospheres, most of them, and again, most of them have surfaces are not subject to a lot of, how should I say this, basically very intense geologic activity. They're not extremely changed over a very long span of time. So observing these bodies actually tells us about the conditions in the very early solar system. One of these bodies is very, very close to us. That's our own moon. And therefore, that brings up to a more, how should I say, practical application of all of this. And that is the moon, being our nearest solar system neighbor, is a place where we can actually do even more science. There's a potential of sending human crews sustainably to the lunar surface and using potential resources on that surface to be able to venture farther out into the solar system and even make astronomical observations, particularly using radio telescopes. So there's actually a lot of reasons to care about small solar system bodies. And again, this presentation specifically focuses on the moon and Charon, and each one kind of figures into this picture in its own way. So first, starting off with the moon, many of you have probably heard that in recent history, with the Lunar Reconnaissance Orbiter and other lunar focused missions, that there's evidence of water ice on the moon. And that is indeed true. Particularly in this case, I'm going to focus on the Lunar Reconnaissance Orbiter, since again, my research actually applies to far ultraviolet reflectance of lunar soils and regoliths, which is meant to back up this research on Lunar Reconnaissance Orbiter. So on board Lunar Reconnaissance Orbiter, there is an instrument called LAMP, and that stands for Lyman Alpha Mapping Project. And in the figure on the right-hand side of this slide here, you're actually seeing some of the data from LAMP plotted, okay? The map that you see here, this image you see here, that's the South Pole Lyman Alpha map. That actually shows the reflectance of the lunar surface in Lyman Alpha. So Lyman Alpha is far UV, that's 121.6 nanometers light that this is observing and is plotted out here. So in these regions toward the southern pole of the moon, very close south pole of the moon, there are a series of craters that are permanently shadowed. That means where they are, sunlight is not actually able to hit those particular craters. And in those regions, the temperatures dip down to very, very low temperatures, basically just a few Kelvin above absolute zero in those regions. And those serve as cold traps. Those serve as regions where very light volatiles, including water molecules, can deposit after a series of hops across the lunar surface. So these areas are traps for certain volatile compounds. So in the shorter UV, you notice in this image that there is not a lot of difference in the coloration there. And that resembles very low albedo, very low reflectance, all right? So in shorter, far ultraviolet, frost absorbs. But in the longer FUV, you start seeing something very different. You actually see that there's regions where that reflectance increases quite a bit. And that implies a roughly 1% water abundance. Now, I want to highlight that as roughly 1%, okay? And that's a key fact here, that is roughly. The reason why that is stated as roughly is because there's actually not a lot of laboratory data to back up these quantifications of the amount of water that's associated with a certain amount of reflectance in the far UV. There was some work done during the mid-1970s on this paper, Wagner et al. Focused on far ultraviolet reflectances. But since then, there's not been an awful lot of laboratory data to back this assertion up. So you could be talking about anywhere from 0.7% to 1.3%. It's very rough measurement. And getting this exact is important for potential future in situ resource utilization applications. In other words, space missions, human space missions, being able to farm this water ice from these regions in the lunar surface to be able to use for rocket fuel, drinking water, etc. So because we do not have a tremendous amount of extant data in the far ultraviolet, the group that I work with has built a chamber to do this kind of work and do it better than what was accomplished in that previous study I mentioned in the 70s. So it's a thing called the Southwest Ultraviolet Reflectance Chamber. And it's an ultra-high vacuum chamber. It gets down to the mid 10 to the negative 8 torr, which is about 10 to the negative 11 ATM. It is used to measure in the far ultraviolet reflectance range, so going from 115 to 200 nanometers. And the way it accomplishes this is it has attached to the chamber a deuterium lamp and a monochromator assembly. The monochromator assembly actually tunes the light that is being shown on the sample in the chamber here to the right far ultraviolet wavelength. So just kind of going through this figure, you have the deuterium lamp, monochromator, there's a series of collimating mirrors to lengthen out the beam to make it a little more uniform over the span that the reflectance measurements are taken. And then in the center of the chamber, there is a retractable sample tray. So that retractable sample tray, you can see that rectangle, it's right in the center there, and there's a line that goes up to it from the lower left-hand corner here. That's at exactly 45 degrees, and that can move the sample into and out of the way of the far ultraviolet light beam. The armature that you see there represented by that, well, basically the smaller rectangle on the longer rectangle that goes around that dotted line circle. That's the detector. That's a channeltron detector that picks up the reflected UV light signal. It can go not quite all the way around the sample, but pretty close to. Not that really matters that much. What matters here is the fact that it can be brought right into the path of the light and then brought out of it, and then sample moved into position can measure those reflectances. This has already been used before my particular studies, which we'll get to here in a moment, on real lunar soil samples. So there was a previous paper by my advisor, Ujjwal Rao, that was published in 2018 on ultraviolet reflectance of Apollo 10084. So Apollo 10084 is a soil sample that was collected by the Apollo 11 mission. Just kind of a fun fact for everyone, when you go through and you look at these sample categorizations, the code numbers that are used on the lunar samples. If it has a 10, it's Apollo 11. If it has a 12, a 14, a 15, a 16, it's from those missions respectively. And then anything that's 700, that's from Apollo 17. And if you paid attention to news, there's actually right now a lunar rock in the Oval Office. Joe Biden requested one for the Oval Office. That one has a 700 code number on it, and that's from the Apollo 17 mission. So if you go to the Cosmosphere, just drive a little north. If you look at the moon rock that's on display in that display case there, that one has a 100 code number on it. That is an Apollo 11 rock that's on display there. It's just something you might want to keep in mind. So the image on the slide here in the lower right-hand side, that's actually that Apollo soil sample 10084. And that's a really awesome part of what I'm doing. We get to work with real lunar soil on this particular experiment. And then the image you see in the upper right-hand corner here, that's actually of the chamber itself. So you can just barely see, but there's that little silver cylinder that's right there. That's actually the deuterium lamp. And then you can't see it, it's hidden behind this mounting here. The monochromator is there. And then the main chamber is right here. Right there, that's a turbomolecular pump. That's what allows us to get down to those very low pressures. So again, that first study that was published by my advisor focused on the ultraviolet reflectance of a very particular soil sample, 10084. We want to be able to do hydrated Apollo soils. And what that means is we actually take a little bit of water and we dose the sample while it's in a chamber with this amount of water, cool it down to a very cold temperature. We actually have a liquid helium cryostat that we're going to attach to this chamber eventually to do this, and simulate these conditions in the permanently shadowed regions at the lunar South Pole. Before we do that, though, we have to keep in mind that there's not an awful lot of Apollo soil to use for this kind of application, especially when you're talking about dosing it with water. We have a few samples from various missions available to us that have been granted to our research group through the channels that are used to distribute out those samples. So it'd be really useful if we could use a simulant to do these studies, if we didn't have to actually use real Apollo soil samples. And there are simulants out there. One of them is a simulant called JSC1A. And JSC1A is a basically a soil that is obtained from a similar environment on the Earth to lunar maria. So lunar maria are those dark regions on the surface of the moon that are essentially dried out lava plains. They are very young material in the history of the moon. And there are places on the Earth where you find very similar materials. One's up in northeastern Arizona. So this material has been obtained for distribution as a lunar soil simulant. Now, there are a few problems with this simulant, though. The first problem is, one, it is from the Earth. It's not from the moon. It is an analog. So there are things that happen on the moon that do not happen on the Earth because, as I mentioned earlier, the moon is a small, airless solar system body. On small, airless solar system bodies, you do not have an atmosphere to block far ultraviolet radiation. You do not have a significant magnetic field to block other forms of cosmic rays. All right, you have a bare surface, and therefore the soils on those surfaces are subject to a process called space weathering. And in particular for lunar soils on space weathering, this space weathering actually causes what's called nanophase iron, which are these very, very, very small separated iron fragments in the outer layer of these olivine crystals that you find in the lunar soil. All right, and then there's also a thing called agglutinates, which are very particularly compacted molten fragments in lunar soil that are the result of many processes. One, meteoritic impacts, and then two, other form, again, other types of space weathering aside from what causes the nanophase iron that can very much change the way these soils appear in the far ultraviolet. Also, even though JSC1A is intended as a lunar mare soil simulant, its composition really is not that close to a mare soil in one very key aspect. So in this plot on the left-hand side of the slide here, I actually have the main chemical constituencies of these samples plotted. Silicon dioxide, titanium dioxide, the aluminum oxide that you see there, the iron oxide, and then of course there's a series of perchlorates and other compounds down the line here. But the black is for Apollo 10084, the yellow is for JSC1A. So two of these are things we've already looked at. It's to some extent in this chamber. The other two are for 14163, which is a Apollo 14 soil. And Apollo 14 landed in kind of a strange region. It wasn't a region, it was exactly a highland. It also wasn't really a mare region either. It was kind of on the border there. And therefore the soil has kind of an odd constituency when compared to being either, again, a mare soil or a highland soil. And in Apollo 70051, which is an Apollo 17 soil, which is another mare soil. If you notice in the constituencies here, the JSC1A, the Apollo 10084, the 14163, 70051, all of those are pretty similar to each other, except for the titanium dioxide content. In terms of the titanium dioxide content, JSC1A is much less than what Apollo 10084 is, or other mare soil samples, including 70051. It's more similar to that 14163 sample that's kind of the oddball sample. Also, when we started looking at this soil, we wanted to get a look at the grain size dependence. Was there any dependency on the size of the grains in these reflectances? So in the image on the right-hand side of the slide here, you actually see the different grain size categories of JSC1A we tried. We actually sieved out portions of our JSC1A available to us. And we did do some testing on that. We kind of moved away from that testing. I'll explain more about that in a moment. But you'll notice that visually it looks like the lower grain size, that sub 38 micrometer grain size, is a lot brighter in its appearance. So in the visible spectrum, there's definitely a difference in their reflectances. And then, of course, I have this magnified view down here. You can see the actual crystals they're contributing. Again, in the larger grain size category, you have this this very dark appearing large grains here. And then there's the unsieved, just raw JSC1A, and that's what we've really focused more of the study on recently. So the paper that myself, my advisor, and others in our research team are working on right now has shifted away from the sieve size samples and more towards just JSC1A in bulk. And so that's what appears like there, just so everyone kind of has an idea of what this looks like. So again, qualitatively, there's dependence in visible light on the grain size. The big question here, though, is does the titanium dioxide have an effect, and does the space weathering have an effect? So in the bidirectional in the SWORC, what we measure is a bidirectional reflectance function as a function of the incident of the emission angle of the reflected light. So these two panes on the right-hand side actually show how all of this plays out inside the chamber. So this box here is the channeltron detector box. And then, of course, right here you have the sample tray, and then there's the incident light intercepting the sample tray there. Theta R, that is the emission angle, as we call that. That is actually the angle of the detector of your observation point away from the zenith, which is marked by that directly vertical dashed line. Theta I is the incident angle. That's the angle of the incident light away from the zenith there. And then G is the phase angle, and the phase angle is the important one. Phase angle is the angle between the direction of the incident light and your observation point. And then your observation aperture is the which is in a solid angle unit, is the theta D there. The PR, that's just the reflected light. So the PI is the incident light, the PR is reflected light. Specifically, that refers to the intensity of those two. So your BRDF, your bidirectional distribution function, is essentially a ratio. It's a ratio of the reflected intensity to the incident intensity, corrected for that cosine negative 45 there, the direction of the incident light, and then the aperture of your collecting area, that theta D there in solid angle. In this particular study, phase angles between 0 degrees, so in other words, just right in line with the light there, to 135 degrees. So basically right in the line path with the sample tray reflected are available to us. And this is what makes this experiment special. We can actually do absolute ultraviolet reflectance measurements here. Previous studies were not able to retract that sample tray away. The sample tray was just kept in the same spot, and they made a guess as to what the incident intensity was they were using, and then did their measurements based off of that. Here we actually get an immediate measurement of the intensity of the incident radiation, and then we do the reflectance measurements. So we actually get, again, absolute bidirectional reflectance measurements. For this study, phase curves, in other words, the actual plot of the intensity as a function of the phase angle, or of the FBRDF, I should say that ratio as a function of the phase angle, were obtained for 121.6 nanometers, in other words, Lyman alpha reflected radiation, 125 nanometers, 130, 135, 140, 150, and 160 nanometers. So spanning both that far FUV range and that longer FUV range. So the preliminary immediate results are that the JSC1A actually does behave very, very differently from Apollo 1084 in ultraviolet reflectance measurements. The Apollo 10084 is backward scattering. All right, so that means that as you move away from the incident light, the reflected intensity becomes dimmer as you start to move angularly away from that incident angle. Whereas JSC1A appears to be more forward scattering. In other words, JSC1A acts more like a really fuzzy mirror. It reflects light at an angle away from the incident, which is rather interesting. Plus, the JSC1A overall appears to be a lot brighter than what the Apollo 10084 is. And I'll show a plot of that here in a few moments. Again, we are moving away from really doing a lot of investigation of grain size because preliminarily we found that the Sieve JSC1A does not really show a strong dependence on the grain size. In other words, the reflectance properties really did not vary that much between one grain size and another in these very preliminary measurements. So actually quantifying this reflectance requires a modeling. You have to actually do modeling to apply to that data to get some very key parameters out there. One of the more important ones being the single scattering albedo, and a number of other parameters too that are very specific to the modeling that you're using. So this is where I'm going to introduce a concept called Hapke photometric modeling. So there is a scientist has worked on many of these orbital space missions and even flybys as well that specializes in remote sensing observations. Bruce Hapke is his name, and he came up with a model to be able to model the reflectance of fine soils in the far ultraviolet or any area of the spectrum at this point back, but we're applying it to the far ultraviolet here. So this model that we use is a simplified version of the Hapke photometric model. And there's a number of factors that go into this model. So first off is the porosity, and that's K. So that K factor actually varies between 0 and 1, with the larger value being a more porous and the smaller value being less porous. On the lunar surface, the soil is actually very, very porous. Of course, the gravity on the lunar surface, the gravitational pull of the lunar surface is only about a sixth of that of the Earth's surface. All right, so the soil is not going to be as compacted down. There's a lot of these, again, various space weathering processes and meteoritic bombardments that allow the soil to kind of be very thinly distributed. You get these fairy castle structures and things like that in the soil. So at the lunar surface, you're really looking at about a 0.8 porosity factor there. In the laboratory, though, that's going to be different. These soils that we're looking at in laboratory, the Apollo soils as well, let alone the JSC1A, they've been on Earth for some time, and they're going to compress down. So for our modeling here, we've assumed a intermediate porosity, a 0.5 porosity there. The W, there is the actual single scattering albedo, the mu I and mu E, those are the cosines of the incident and emittance angles respectively. And then that P is a function of G. So that G is a phase angle. That P of a function as a function of G is what's called the Henne-Greenstein single scattering phase function. It's a double-lobed function. It is empirically derived. So in other words, this is not, this function actually comes from observations of fine grain samples. This is not derived from any firm theoretical principles there, should we say. It is all derived empirically in this case. It's a very long derivation. I do not have it all here. And if you want more information about these equations, where they come from, how they're derived, I encourage you to go to the book by Bruce Hapke. which is a theory of reflectance and emittance spectroscopy. There's a lot there to go through, but it explains it very thoroughly. The important thing about this scattering phase function, though, the P of G function, is it has these factors C and B. And the C determines the asymmetry of that function, whereas the B determines lobe size, shape, and size of the function. All right. The important fact there is the C part of that, because the C part of that actually determines forward or backward scattering. A positive C value implies backward scattering, whereas a negative C value implies forward scattering. The M factor there, last factor there in the model, that is the interparticle multiple scattering. There's a number of things going into that. I've not included that in this slide, but basically what it does is it includes the factors of how light scatters between the particles themselves in your soil sample. And I think my clicker went out. Okay, so okay. I wonder why everything froze up all of a sudden on me. There we go. Okay. Okay, so the results of all this. The results of this are that the compared to Apollo 10084, indeed the JSC1A is for very much very much forward scattering. So all of these points in this plot on the on the right hand side that you see here, those are all for JSC1A in some various shape or form. And notice they all have a negative C value. That definitely does imply a forward scattering. These points up here are all for Apollo 10084. By the way, I will stress these are preliminary. Again, these are all separated by grain size, and they're very rough modeling results. We actually are right now doing the unsieved JSC1A, just bulk JSC1A. And the results are a lot neater there. And again, it's a work in progress, but we're actually seeing something a little more interesting than that. But I'll save that for a paper that will be issued on this eventually. But the Apollo 10084, notice the positive C values definitely on the backward scattering side. Now, this line that you see here, that hockey stick curve, that is an empirically derived relation between the C and B factor in that approximation. And it was obtained in a study that was done by Hapke that examined, I think if I remember right, about 495 different grain samples. And it found that the samples generally fell in the C versus B along that curve there. So the Apollo 10084 fell very well along that curve. The JSC1A, at least in what I'm showing here, did not. However, again, there's newer data that we are getting on the unsieved JSC1A, just the bulk JSC1A. It's actually bringing it a little closer to that curve. And we'll see what actually comes out of all this. Again, this is all very preliminary. Going over here and using the result for single scattering albedo from the modeling, we find something very, very interesting. And that is that the JSC1A, as I mentioned earlier, is quite a bit brighter, but also JSC1A shows a distinct blue slope. In other words, it's more reflective in the far ultraviolet that is in the near than that longer ultraviolet range there. And that's very interesting, because it was thought at one time from a series of studies that the far ultraviolet properties of the actual Apollo soils, lunar surface soils, would show spectral bluing, in other words, a greater reflectance due to the presence of the nanophase iron, that space weathering aspect that I talked about earlier. And what this implies is that you still see spectral bluing, and not only do you still see spectral bluing, but a much more dramatic spectral bluing in a Earth-based soil analog. And that's a little bit surprising. That's somewhat unexpected because, again, the conventional wisdom was that the spectral bluing would be more pronounced for a real lunar soil sample. And that does not seem to be the case here. Notice that you have all these purple points. That's for Apollo 10084. The slope is -4.2 times 10⁻⁴. All of these are in the 10⁻�3s, and all of these are for JSC1A samples. So that's probably one of the more interesting things that's come out of this. One thing, though, we do have to figure out is why for these differences? Why is JSC1A more forward scattering than Apollo 10084 is, which is backward scattering? And why is it that there's still spectral bluing there, even though there's presence of this nanophase iron that should very much absorb that should very much be reflective of a lot of this Lyman alpha band stuff. So there's still a lot of work to be done on that as to really why this is the case. We have our ideas. A lot of it probably does stem from the space weathering characteristics. In case of the overall brightness of the overall increase in single scattering albedo, that's probably due to the space weathering, because the nanophase iron is a darkening agent. So that is probably due to the nanophase iron itself. But the difference in blue slope, that's interesting. And that's one we're really going to have to think about as to what the reasons are for that. So on the moon side of things, I'm going to shift to the Pluto side of things here. The conclusions and further directions. Basically, JSC1A was very well designed as an engineering analog, but from our studies here, we can tell you that it's not really usable for far ultraviolet spectrophotometric studies. The ideal spectrophotometric analog would include nanophase iron and other space weathering features. And the further work after this will try to solve some of this by eliminating one possibility. And that is that, again, the JSC1A is a low titanium dioxide content soil, whereas the Mare soils were a higher titanium dioxide content. So if we're comparing this to 10084, we need to eliminate the possibility that some of these differences are due to the titanium content. There is another simulant, and I didn't plot out its constituencies here. I didn't really have time to make up that plot, but it's LMS1. And LMS1 was obtained from a slightly different deposit than what JSC1A was. And LMS1 actually has a higher titanium dioxide content. So our next step is to do more measurements on the LMS1 and then go on to the preparations for the hydrated Apollo soils. So moving on to the other half of the work I do. And the other half of the work I do is for Pluto's largest moon, Charon. So Pluto and Charon, just as a review for everyone, they form a double dwarf planet, essentially. The center of gravity between the two is very far outside of Pluto and Charon both. So they kind of orbit around this common center of gravity, and therefore they're really kind of a weird system. And when New Horizons, the probe that passed by Pluto back in 2015, imaged Charon, its multispectral visible imaging camera, MVIC, showed this reddish region toward the pole there. And that was very interesting. And ground-based observations never really showed that much of details on Pluto, let alone Charon. And yet when you get to Charon, you see not only these very marked surface variations, which imply very dramatic activity in terms of impacts and rift formation, but you also see this very distinct red region toward the poles. Well, a study was published by Grundy et al. In 2016 that attempted to explain this reddish region toward the poles. And the explanation is that plutonium methane that actually accretes away from Pluto during the warmer season at Pluto deposits toward Charon's poles. And basically what happens is temperatures are higher toward the equator here. And they, again, as I mentioned on the lunar surface, the methane tends to hop towards the poles where the temperature is colder. And the red color of this deposit is due to refractories of the photolyzed methane. So in other words, methane is bombarded by Lyman alpha radiation. I'll show more about that in the next slide. And it is converted into these more complex refractories that have that distinct red color. So the open question here, before really saying, you know, what's real and what's not on this hypothesis, this theory, is that what fraction of the methane is photolyzed by the IPM Lyman alpha under Sharon-like conditions? And there's where you have to do laboratory experiments to figure that out. So just a little bit of an overview in more detail of this dynamic photolysis process at Sharon. So again, plutonium methane, and I think the bad, nope, I'm good, okay. So the plutonium methane deposits towards Sharon. And then there's this Lyman alpha radiation from what's called the interplanetary medium. Now, the interplanetary medium is basically the background of hydrogen and then some dust that is between it's within the solar system, between the planets themselves. At the Earth and Moon, the IPM Lyman alpha background is almost nil compared to the Lyman alpha band radiation from the sun. Okay. And however, when you get out to Pluto and Charon, that's not the case. Pluto and Charon, the Lyman alpha radiation from that IPM is actually far more substantial than what it is from the sun, and therefore that's very likely the main contributor to any Lyman alpha, but at least for UV Lyman alpha facilitated photolysis of methane. So you have the methane that goes toward Charon from Pluto, and then the Lyman alpha radiation as well. As the methane deposits at the poles of Charon, there is this constant renewing of the layers as the Lyman alpha radiation photolyzes. So you basically get this constantly growing layer of a mixture of pure and photolyzed methane. All right. And a key parameter controlling this refractory synthesis, which is described by this relation here. So this relation here again talks about the concentration of the photolyzed methane in that layer. So that's that derivative of eta over time. And you have the incoming flux of the methane. From that, you have the Lyman alpha photolyzed portion described there, and then the portion here that's the fractional brought away in the layering process. So the key parameter controlling this refractory synthesis, assuming a steady state, meaning that this is essentially equal to 0, is the phi value here. And again, that's that ratio of the methane accretion flux to the interplanetary medium Lyman alpha flux. So in the laboratory, what we do is we have another chamber. This is in a different laboratory from the one that the SWERC is in, where within the chamber, it's brought down to very high vacuum, and a very small amount of methane is introduced into the chamber and frozen down to -10 Kelvin, very, very cold. And this is meant to specifically simulate what is going on at Charon, because that is the estimated surface temperature toward the poles of Charon during the time period of this methane deposition. All right. So within the chamber, there is what's called a QCM. QCM stands for quartz crystal microbalance. And that quartz crystal microbalance is a small semiconductor crystal set that vibrates at a certain frequency and can be measured, of course, to a very good precision. And as the methane deposits on that frequency starts to slow down. It starts to become a much longer frequency, all right, a much lower frequency. And therefore you can kind of go through the calculations and calculate how much mass has been deposited on that crystal based off of the change in that oscillation. As the methane is being deposited onto the QCM, at times a Lyman alpha light source, so that's this microwave attenuated hydrogen helium lamp here. Lyman alpha light source is beamed onto the deposit on the QCM, and you can actually measure the rate at which the deposition changes with this irradiation, etc. The flux of the Lyman alpha radiation is measured by this grid that you see here and this photodiode. So in the earlier experiments, we actually used a gold-coated wire grid to measure the flux of the incoming radiation, but the problem is that that's a very rough way of going about doing it. We updated it with a photodiode later, but there's actually some other challenges with photodiodes. So we've had to do a little bit of work kind of interpolating what the actual intensity of the Lyman alpha band is here, which is what my contribution to this particular project is. I'm going to be a co-author on a couple of papers that have to do with this work. And I help to basically constrain what that Lyman alpha band radiation is. So when you actually go through, you go through and you take this data, and taking this data, you actually get a curve of the mass loss versus temperature. So pre-experiment, there's a deposition of this methane, and then you go through the experiment, and with varying different phi values here, you actually get a certain amount of this photolized methane. In other words, certain compounds, including ethane, and then some more complex things remaining in the deposited ice. So when you melt the ice, when you bring the temperature up, if there's nothing there, if it's pure methane film, it just goes straight from total mass present to nothing. But if this has been photolized, if there's these photolysis products there, you get these kind of bends and knees in the profile. And so that implies that there's these photolysis products there. And we actually measure the amount of the photolysis product based off of these curves. And we correspond that to the incident flux that we used in each of these experiments to obtain that phi value. So fitting of the yield that we see here versus the phi that's used, we actually get a cross section of that Lyman alpha photolysis process. And again, this is a big question mark that was left in the Grundy paper and the Grundy hypothesis on this deposition of these products at Sharon's poles. What is the actual cross section of this photolysis? And it appears to be somewhere in the neighborhood of 9 times 10 to the negative 18 centimeters squared is that cross section. So if phi is equal to 1 at the poles, that equates to a roughly 40% photoconversion of these products here. That revises some of what Grundy proposed in the paper, and not only that, when it's included in our own exospheric modeling, which has been performed by other team members with me, mainly Ben Teolis, it implies that there actually is more to this story than even what Grundy purely is talking about in his paper. And that is that there's actually other sources, other space weathering sources that are contributing to this reddening here. But again, there's more information on this for other days. Another key point of going on forward beyond these studies, expanding on these results, is that there's a notable increase in these complex refractories at smaller phi values. So in other words, where that incoming methane flux is much smaller than the Lyman alpha flux. So in other words, there's a much greater photolysis happening than the pace of actual methane deposition. And you can see this here with this very long curve here of all this stuff that's taking a long time to melt away. There's way more complex refractories. And again, there's a lot more investigation will be needed to determine what exactly those refractories are and what role they have in the overall reflectance. So in conclusion, the methane to refractory conversion is very much feed dependent, as we saw there by the increase in complex methane photolysis products with decreasing feed. The methane to refractory conversion cross section in conditions current accretion and irradiation as occurring on Charon have been determined experimentally here. So the further directions are again incorporating this into the modeling, which again is in progress and frankly wrapping up right now. And then my next project on this, my actual contribution for result in a first author paper for me will be constraining the color versus yield depends. So in other words, actually looking at those refractory products in terms of their reflectance. So basically doing what I've been doing in this work on the lunar samples on these refractory results from these experiments, and getting the various albedo, color constants, etc., from those products, and then trying to correlate that with what we see in the MVIC images from New Horizons. So I have a couple concluding slides here because again, there's two separate lines of work that are described here. Oh, so this is more on the moon stuff. There's the funding credit right there, but more information on the Apollo 10084 findings can be found in the previous paper by my advisor, Ujjwal Rao. That's far ultraviolet photometric response of Apollo soil 10084 from 2018. As for the Pluto work, I encourage everyone to take a look at that paper by Grundy et al., W.M. Grundy et al. The formation of Charon's red poles from seasonally cold trap volatiles, which was published in Nature some time ago. In fact, did I get? No, I didn't get it back in 2016, November 2016. Then there's another line of thanks there to a number of my colleagues who helped me with the lab experiments, and also some that work on the more science aspects of it away, the theoretical aspects of it away from the laboratory. That's for both projects, by the way, in this listing. The Pluto work is supported by NASA NFDAP grant numbered here, and in Southwest Research Institute internal funding. All of this is under a thing that we call CLASSI, the Center for Laboratory Astrophysics and Space Science Experiments. Basically, we are a group of these UTSA and SWORI scientists that work on experimental investigations of these planetary surface processes. You can find more information about that at https://classlab.space.swori.edu. For anyone that is looking to go on into graduate school and is interested in this program, certainly I welcome questions about any of that. Basically just look up UTSA, University of Texas, San Antonio Physics. Actually, most specifically, University of Texas, San Antonio Space Physics or Space Science, either term will work, and that'll bring up a lot of information on that. And so with that, I will take any questions.
Yes, thanks. That was a very nice presentation. I think we have about a dozen people online and almost as many here. So questions, anybody, please unmute yourself or go ahead.
So I've got a question. You mentioned that one of the reasons that we expect the lunar soil samples to be so different is because they've been bombarded by a lot of ultraviolet radiation. Have you considered taking one of these simulant soils and putting it under an ultraviolet source for a month?
Yeah, very good question. Not as much the ultraviolet, it's actually more the cosmic rays and things like that, although ultraviolet would contribute. Yes, that is being considered, and the way it's being considered is we are actually working up on a follow-up chamber to the SWORC chamber. All right, so that chamber, the SWORC, that is a very roughly put together experiment, to say the very least. So to give you a little bit more of a personal background on this, I started on this project along with many other people that were somewhat new to the project. They had some technicians leave, and there were some other change arounds. So a lot of us had to kind of relearn everything that had been learned before on using this equipment. And there's a lot of things that can be improved with it. We wound up interrupted by the COVID pandemic, obviously. After the COVID pandemic, we decided to go through and repair some issues with the equipment and get some things really well put together. So a lot of the very, what I call high fidelity work on the JSC1A, which is not on the sieved samples, it's not the data I showed you, the much better data that I'm still working on right now, that has only been done over the past 2 months, really. And it's much better data. I'm glad we went through and did all the work on the equipment, but that piece of equipment requires a lot of tender loving care. And therefore we are working on a new chamber called SWORC 2.0. And SWORC 2.0 will actually have ion guns and other radiation sources attached to it, that we can do those kind of studies and be able to see how bombarding these samples with not only ultraviolet light, but also, again, these ion sources, things like that, will affect the reflectance. And we may find, and again, there's other ways of making rough determinations with this, but we may find that it does have an effect. We may find that there really doesn't have an effect, that just simply bombarding an Earth-based analog is not going to necessarily change that much. And we still have to, of course, find out what we get from that LMS1 simulant, because there's a lot of questions there too. It may very much depend on the exact soil and the exact preparations used in making that soil. So there's still a little bit of work to be done, but there's enough work now to where we can at least determine that you will have to use the real lunar soil for the hydration studies, and that you will have definite differences due to space weathering in some way, shape, or form. So.
All right, any other questions? It doesn't look like it. So thank you, Caleb, once more. And we'll meet again next week for the Welcome Back event. And then in 2 weeks, we have the next physics seminar. If you like, you can unmute yourself and clap rather than just either way. Thank you.
You're very welcome. Yeah, thanks for the claps, all of you that put claps up there in the picture. Yep.
All right. See you all next week.
Yep.
Have a good rest of the day.
Bye,
Thanks
everyone.
very much. Take care.
Bye.